Hey guys, welcome back to Cooker Chem Tutoring. I'm Austin and I'll be running through part 2 of problem set 12, Lewis structures. All right, number 5 says describe how formal charges are used to choose between possible molecular structures. So at the end of the last video, we kind of learned how to actually figure out what the formal charges are. But using formal charges is extremely useful when we're choosing between Lewis structures. So the best Lewis structure will always minimize formal charge, okay? That's the key. We don't want to have charge. Remember when I was describing charges kind of like weight, and we want to spread the weight, like a high heel. We don't want to have a high heel. We'd prefer to have a clown shoe, because it's hard to have so much pressure on one area, on one small area. When we can spread it out, that's a lot better. And in the same way, we don't want to have a lot of charges. Charges provide that kind of weight. And placing charges will also help when we put the negative charge on the most electronegative atoms. That kind of answers the second part down here, is when we put the negative charge on the most electronegative atom, that actually helps stabilize the Lewis structure as well. So in accordance with minimizing formal charge and putting the negative charges on the most electronegative atoms are going to help us create the best possible Lewis structures, the most stable possible Lewis structures, and in the end, the most accurate. Okay, and so part B, kind of re-emphasizing, we want to make sure that the negative formal charges, so anything that's negative 1, negative 2, negative 3, is on the most electronegative atom. And that'll help with the stability of the Lewis structure, because think about electronegativity as wanting to have electron density around yourself, right? It's because, like, let's take oxygen, for example. Oxygen has 8 protons, so I'll just put, let's see, it's kind of hard to, let's see, depict all these, but just pretend that all of these are protons and they're all positively charged, okay? And it's got a 1s, so here's my 1s, and then it's got a 2p, or 2s, sorry, and then a 2p. Okay, as opposed to something like, let's say, chlorine. Chlorine's got like an extra, chlorine would have another one of these guys, right? And so because oxygen's nucleus is so much more exposed to the outside world, and it's positively charged, right? It wants to pull electron density towards itself. And so, and we talked about this in polarity, right? Same idea happens when we're talking about formal charge, because we want to put the negative charges on the most electronegative atoms, because they're going to pull that density towards themselves. So that's why we do that with Lewis structures. So now in part C, they actually ask us to add formal charges to these Lewis structures. Okay, and which of the following structures are resonance structures of each other? Now, if you remember, excuse me, I'm kind of sick today. If you remember from the last video, we talked about how to assign formal charges, and we always said it's want minus have, okay? Oops, have, okay? The want comes from where is it on the periodic table? So here's PT, periodic table, meaning how many valence electrons does it like to have assigned to it, okay? And then have is based off the Lewis structure, okay? Whoops, Lewis structure, okay? So, for example, let's take this nitrogen right here. Nitrogen is in the 5th group of the periodic table, okay? So that means it wants 5. So I'm going to put a 5 here, okay? Because that's what it normally wants assigned to it. And then what it actually has will depend on what we have on the Lewis structure here. So here, remember, we count lone pairs, both the electrons in lone pairs, as belonging to the nitrogen. So it has a 2 so far, and then we've got 1, 2, 3 different bonds here, okay? And we only count, remember, each bond is made up of 2 electrons. And so we only count one of those electrons as actually belonging to nitrogen. And so since we have 3 bonds, we're going to say that there's a total of 3 there, okay? And then that 2 plus 3 is obviously 5, okay? And 5 minus 5 is 0, which means this nitrogen right here has a formal charge of 0. And you'll notice that anytime you see a nitrogen with a lone pair and then 3 different bonds, it's always going to have a formal charge of 0. Now, typically, we actually leave out anything that has a 0 formal charge. We really only indicate those that have a different formal charge that's not 0, or you'll hear it called non-zero formal charges, okay? So in part A, let's look at the next nitrogen. Remember, it still wants 5. Okay, but now it doesn't have any lone pairs, but it does have 1, 2, 3, 4 bonds, which means now that's going to be my 5 minus 4, which is a positive 1. Okay, so I'm going to put positive right here on that nitrogen. Now, I didn't emphasize the second part of this question. The second part of this question is asking us which of the following structures are resonance structures. So that was kind of an intro to formal charges on these structures. But let's figure out if we can eliminate any of these from the options. Okay. So remember, a Lewis structure has to have everything bound the same way. It has to be exactly bound the same way. The only difference will be that the electrons can look different. Okay, so let's look at this structure and see if there are any other ones that look almost exactly like that. Okay, remember they have to be bound the same way. Okay, if we look at D here, it looks like it could be bound the same way, but notice that we have an extra hydrogen here. Okay, so that actually can't be a Lewis structure. So I'm going to say, well, at least so far, that A cannot be a Lewis structure with D so far. Okay, let's see B. Does B look like anything? Okay, it kind of looks like E, but B has this extra H, so it doesn't have a resonance structure with B either. Okay, let's see C. C has this N, and then 3 carbons, and then 6 hydrogens. And if you look on E, it actually looks like it could be the same. In fact, this is the same, that has the same structure. And so we could say that E and C are possible resonance structures. We'll double check, but for right now, we're just going to assume that these two are going to be the Lewis structures that we're going to work with. So at least so far, let's see if there's a third one. So if we look at this one, I don't see any of this. I don't see this N to 2 H's structure on any of the other ones. So I'm going to actually X this out because I'm assuming that I'm going to be looking at stuff at the structure that looks like this. And you'll notice that this remember, we kind of eliminated that because it didn't look like A, and A doesn't look like anything. And B also didn't look like anything. It almost looked like E, but we have an extra hydrogen here, okay? So it looks like E and C are going to be our Lewis structures. So now let's just make sure that on these Lewis structures we can assign the formal charge. Let's see. It looks like they actually wanted you to do the formal charge on all of them. So let's go ahead and do this. But you know that E and C are going to be the resonance structures of each other because they have the same structure. Okay, they have I'll just go ahead and put a circle around both of them. They have the same structure, but just different arrangement of electrons, okay? So now part B, we put our one formal charge here. Let's look at the carbons here really quick. Remember, carbon wants 4. And anytime you see it bound to 4 things, remember, we only count half a bond. So it's actually going to be just -4, and that's going to be 0. So I'm going to leave those as 0 and not put anything there, just assuming that they're 0. So, and then part B here, if I look at the nitrogen, remember, nitrogen wants 5. I'll put want minus have. Wants 5, has 1, 2, 3, 4, 5. -5 is 0. Okay, so this is a 0 formal charge. I'm just going to leave it out then. This nitrogen right here, it doesn't have that lone pair, so I'm going to expect that this has some sort of formal charge. So let's see. It's got 1, 2, 3, 4 bonds, and no lone pair, so that's going to be 4, and that's going to be, oops, not a 0, a +1, +1. So that nitrogen right there has a +1 formal charge. And I'm just going to put plus sign right there, okay? I'll even circle it so it's kind of a little bit more obvious. All right, and then we said carbon. Carbon wants 4, so I'm going to put carbon here. Wants 4, okay, want minus have. Okay, in this structure, it's got 1, 2, 3, 4, so I'm going to say -4. That's a 0, and you'll notice that it's going to be the same for all of them. And anytime hydrogen is in a structure, you're almost never going to have, it's never going to be charged. It's never going to have a formal charge, just because it only needs 1. It only makes 1 bond, so it typically ends up being 0. So this nitrogen is the only formal charge that's non-zero. All right, letter C now. Same thing again, looks like, except this time we've got 2 lone pairs to this nitrogen. So now we know it wants 5, but in this structure, what does it have? It's got 2, 4, 5, 6. So I'm going to say 5 minus 6. That's a -1 this time. So now it's got a -1 formal charge. Okay, so I'm going to put -1. I'm just going to put a minus sign, which is pretty typical, conventional that we do when we just write formal charges. We just put the minus if it's just 1, or a plus if it's just 1. And then this nitrogen, it's got 1, 2, 3, 4. So I'm going to put a plus sign right there because it wants 5 but has 4. Okay, and then each of these carbons, you'll notice that this carbon has 1, 2, 3, 4, and then each of these carbons also has 4. So almost rare occasion, unless you see a carbon with a lone pair, it's usually not going to have a non-zero formal charge. Like I said, unless it has a lone pair, then it will have a non-zero formal charge. So anytime for the rest of these structures, I'm just going to kind of ignore carbon unless it has a lone pair, okay? All right, so now on part D, I'm going to look at this nitrogen again. Remember, wants 5. It's got 1, 2, 3, 4, 5, so -5 is 0. This one has 2, 3, 4, 5, so that's also 0. And then those carbons are all 0, so actually there are no formal charges. No, I'll just put no formal charges on this one. Okay. And then now E, I've got, remember it wants 5, so it's got 5 minus, let's see, 2, 3, 4, 5. So 5 minus 5, that's 0. So that's going to be 0 formal charge. And then this guy right here, this nitrogen right here, is going to have a +1, right? because we got 3 or 4 bonds, and it doesn't have any lone pairs. Now I said I was going to ignore the carbons, but look at this carbon. This carbon has a lone pair now. So remember, carbon, it wants 4 and has, in this structure, it's got 1, 2, 3, 4, 5. So it's got 4 minus 5. That's going to be a minus 1. So I'm actually going to let me clean up this mess here. We're still circling this guy because it's the resonance structure. This was a +1, and this carbon is a minus. Okay. All right, last one on F. Looks like nitrogen here has its 2, 3, 4, and 5, so I'm going to leave it there. 2, 3, 4, and 5. And then carbon doesn't have any lone pair, so I'm going to ignore it. So that actually doesn't have any formal charges either. Okay. So that's your answer. Here are your formal charges. Just make sure that it's obvious which element you're indicating the formal charge for, and then just circle the ones that are resonance structures of each other. Okay, I hope that made some sense. All right, number 6, use formal charges to determine which resonance form of the falling ions is preferred. Okay, so now this is where resonance, like using resonance and formal charges actually helps us to determine how these will actually bond with one another. So here what they want you to assume is that carbon in this structure will be on the outside, nitrogen in the middle, and then oxygen on the outside. And then remember our Lewis structures rule. We're going to give everybody an octet and then count the number of electrons I need. So in this case, I have 4, 5, 6, plus 1 is 7. So I'm going to say 7 plus 9, that's going to be 16 valence electrons, okay? So then what I'm going to do is see what I have in my Lewis structure. So I've got 8 here, that's 16, 18, 20. Okay, so now I know I'm going to have to erase at least 4 total, a net loss of 4. So what I'm going to do is I'm going to make a bond between nitrogen and carbon, because I know so far, if you want to know why I'm doing that first, is because if you look at the formal charges, there's a -1 on this oxygen, there's a -1 on this, -1 on this nitrogen, and a, let's see, well, yeah. So once we get the correct Lewis structure, this will make more sense. I'm going to make this triple bond with nitrogen, just to see if this works, and then another one with nitrogen right here, okay? Now, if I do this, the formal charges on this carbon has 2, 3, 4, 5. Okay, so that has a -1 charge here, so I'm going to put a minus sign on that. Whoops. Let's go ahead and just erase those. Okay, it's got a minus charge. This nitrogen, if you do the formal charge correctly, has a plus charge. Now, some people would be like, well, can this make another bond to make a quadruple bond to minimize formal charge? Remember, we wouldn't do that because it would break the octet rule, right? So we have to keep those charges separated. And then this oxygen has a negative charge. So kind of funky looking, right? Got a negative formal charge, a positive, and a negative, and we can't really reduce them down anymore because we would break octets. So this is kind of the most preferred Lewis structure for this ion. So now I need to actually draw a resonance structure for the structure, because this could be arranged differently, right? So I'm going to bracket this because it is a Lewis structure and has an overall -1 charge, right? If we add -1 plus 1 minus 1, that gets us a -1 formal charge. And then I'm going to draw my double-headed arrows. Okay, and now I had a triple bond here and a single bond here. What if I just moved one of those bonds over, or not? I'm not necessarily moving those bonds over. What I'm doing is actually bringing this lone pair down and then kicking this up to be a lone pair. So in this case, carbon would have 2 lone pairs, and then a double bond to nitrogen, double bond to oxygen, just like this. Okay, so this is another possible Lewis structure that we haven't considered yet. So now we got to look at the formal charges. Nitrogen is still +1, but now if you look at oxygen, remember it wants 6. In this structure, it's got 2, 4, 5, 6. So I'm going to put 6, and that's a 0 formal charge. So in this case, oxygen is actually pretty stable. It doesn't have the -1 charge, which actually in this case could be a bad thing, because oxygen in this structure is the most electronegative atom. So in theory, whichever element, in this case it's going to be carbon, right? You can already tell. It's not going to be a good Lewis structure because it doesn't have the negative charge is not on the most electronegative atom. So what we would do here is let's calculate the formal charge on this carbon. It's actually going to be a -2. Okay, and having a big number like that is the opposite of minimizing formal charge, right? We've now maximized formal charge in this case. And so this is, even though this is a possible resonance structure, it's not a very valid resonance structure. It's not going to exist a lot. It's not very energetically favorable compared to this one. Okay, so now we got to figure out which one of the other ones here, and this one or this one is going to be another preferred resonance structure. So I'm actually going to circle this guy. And actually, let me just X out this guy right now. We're actually not going to do that. The reason is because remember one of the rules of drawing a Lewis structure is that you want the center atom has to be the one that makes the most bonds, okay? And in that case, if oxygen was the middle, we'd actually have a ton. In order to accommodate the bonds, we would actually have to either expand octets, which we can't do because we're in the second period of the periodic table, or we would have to have a very high formal charge count. And so that's another reason why it's not very favorable to have a center atom that doesn't make very many bonds, okay? So I'm actually just going to exit out, and they actually exit out in the key as well. So I don't feel too awful for not showing you how to do that. It's just not going to be very, very pretty, okay? So now I'm going to do the second structure here, though. So I'm going to say N, carbon, O, and then give everybody their octet. Okay, remember we want 16. Here's 16, 18, 20, 22. So, sorry, 8, 16, 18, 20. So we've got 4 extra again. So I'm going to make my a bond right here and a bond right here. Okay, just like we did in the first structure, and then bracket this because it's got a -1 charge. Now, if we look at carbon, remember carbon wants 4 and has 1, 2, 3, 4, half of each of those bonds. And so this is going to have a 0 formal charge, 0 formal charge. And then nitrogen wants 5. It's got 2, 3, 4, 5. So it's actually pretty happy too. So it's got a 0 formal charge. And then oxygen, is got a -1 formal charge. Remember, it wants 6, and it's got 2, 4, 6, and then 7 here. So that gives it a -1 charge. Now, this is the most stable one. The reason is because not only have we minimized formal charge, but the most negative formal charge is on the most electronegative atom. So this is actually an extremely stable structure. And if we draw a resonance structure for this, though, remember we moved one of the lone pairs down here to make a bond and then kick that one up. So we got 2 lone pairs on this nitrogen, double bound to carbon, double bound to oxygen. And again, we have a 0 on the carbon, but now we have a 0 on the oxygen, right? 2, 4, 5, 6, because it usually wants 6. But in this case, now we have a minus on the nitrogen. So this is a valid Lewis structure because nitrogen is relatively electronegative, but it's not the most stable, right? This one is the most stable because it's got the negative charge on the most electronegative atom. Really quick, I will draw the CON minus, but not because you would need to know it, okay? I'm just going to draw it just to show you where these charges would be, right? So if I do this again, I'm going to have to draw a triple bond here again. Okay, and a single bond there. Look at the formal charge on oxygen. Oxygen wants 6, right? And it's got 1, 2, 3, 4, -4. That's a +2, okay? As opposed to this nitrogen wants 5. It's got 7, so this is a -2, and then we've got a -1 on this carbon. Okay, so this is actually the reason that they probably don't want you to even draw this one. I don't know. At least in my key, it's X'd out, like they didn't even want you to do it or something. I guess maybe they do want you to do it. I don't know, but in this case, yeah, it has an overall minus charge, but it's ridiculously unminimized, right? There's this split charge over here. Even if we drew a resonance structure for this, we'd have carbon it would now have a -2 charge. Oxygen would still have the +2, and now the minus charge would be on this nitrogen if we did this structure. Okay, so it's just not very favorable. It's not even going to exist because of this formal charge. These formal charges are not minimized at all. So part B, we say which of the following Lewis structures below contributes most to the bonding in C and O. Okay, so remember, when they're asking which one contributes the most to the bonding, it's the one that's going to have the minimized formal charges, okay? So what you got to do on each of these is figure out what the formal charges are. So remember, carbon wants 4. In this case, it's got 2, 3, 4, 5, 6. So that's going to be a -2, right? 4 minus 6 is -2. Nitrogen, in this case, it's got a +1, right? It wants 5. It's got 1, 2, 3, 4. And then oxygen, actually, in this case, has a +1 because it wants 6 and has 2, 3, 4, 5. So it's going to be 6 minus 5. Let me just write these up here so you know where I'm getting these from. So that one is likely not going to be one of the bonding, one that contributes most to the bonding because it doesn't minimize the formal charge. So If we look at part B now, remember carbon wants 4, so it's got 2, 3, 4, 5. So now we've got a -1 charge, on the carbon. Nitrogen still has that +1 because it doesn't have any lone pairs, and oxygen actually has a 0 in this case. So this could be a structure because it does relatively minimize the formal charge, because let me just make sure you understand why it's 0. So remember, oxygen wants 6 because it's in the 6th group in the periodic table. We've got 2, 4, 5, 6. So that's going to be 0 formal charge. Okay, so relatively, this could be one of the ones that contributes most to the formal charge. The only thing I see here, though, is that the negative charge is on the least electronegative atom. So maybe there's one here that will actually have it placed somewhere else. So here are each of the nitrogens here, as you can tell, because they don't have a lone pair. They have 4 different bonds. They're going to be positively charged. Carbon wants 4. In this case, it has 2, 3, 4, 5. So it's going to have a -1 charge. And then this oxygen wants 6, and it's got 2, 3, 4, 5, 6, actually. So in this case, this is 0. Again, this could possibly be another Lewis structure. Kind of funky how this still worked out, right? It's still, we actually have to add a radical in order for this to work out on the oxygen. But still, this could be a structure, but we're not sure. We have to look at this last one. So, carbon wants 4. In this case, has 1, 2, 3, 4. So it's got 4 minus 4. That's going to be 0. And then we knew the nitrogen had a +1, and then oxygen wants 6 minus 2, 4, 6, 7. Okay, so this is going to be a minus. So now, not only is this one minimized the formal charge like B and C, it's actually put the negative charge on the most electronegative atom. So I'm going to circle D. D is the correct answer for 6B. Okay, hope that made some sense. Hopefully you're kind of getting the hang of assigning formal charges too. They can, at first they're a little bit difficult, but once you get the hang of it, it actually gets pretty easy, right? If you just know where the element is, which group it is on the periodic table, you know how much it wants, and then if you know how to assign it on the Lewis structure, you know how much it has, and then just take the difference. All right, 7A says, why do C, N, O, and F atoms covalently bonded molecules and ions have no more than 8 valence electrons? Okay, and this is simply because they're in the 2nd period, okay, and they can't expand an octet. They don't have any more. They can't ever have bigger than 8 electrons in their valence shell. So you can only expand once you hit the 3rd period, because when you hit N equals 3, when n equals 3, L can be equal to 0, 1, or 2, and 2 are d orbitals, right? So you have access to 3 d orbitals when you're in the n equals 3 shell, or the period, or the 3rd period of the periodic table. And because they're not there in the 2nd period of the periodic table, they can't do that, right? That's limited to L is equal to 0 and 1 when n is equal to 2, and you can only have s or p orbitals open to you. All right, part B says, do atoms in row 3 below always expand their valence shell? Explain your answer. Well, and we've talked about this before. They don't, right? When we're looking at making a Lewis structure, we always choose the element that can make the most bonds without expanding the octets. Why? Because it costs energy, okay? D orbitals are in higher energy orbitals, right? They're in a higher energy subshell. And so if we really need them, we'll access them, but it does cost energy. And so they're not always going to do it, only if necessary. If it can accommodate all the bonds, otherwise it's not going to expand it, okay? So no, the answer is no for that one. All right, letter C says the compound Cl2O2 may play a role in the ozone depletion of the stratosphere. Draw the Lewis structure of Cl2O2 based on the arrangement of the atoms to the right. Do either of the chlorines have an expanded valence shell? Okay, so we know that chlorine, hopefully you can see on the periodic table that that's in the 3rd period. Okay, so it can expand its octet potentially, and they just want to know if it does in this structure. So we're going to assume that the chlorine is the green one. So I'm going to draw my skeleton here, and then give everybody their octet. And then count my valence electrons to see if they match. So I've got 2 times 7, okay, plus 2 times 6. That's going to be 14 plus 12 is going to be 26, okay, valence electrons. And I'm going to see if this structure has 26. So I'm going to say 1, 2, 3 times 8, so that's 24, 26. We actually have the correct number of valence electrons here. So now what we need to look at is, are we going to have to expand, or are we going to have to change or make bonds according to formal charges? So if you look at this oxygen, remember oxygen wants 6 in the periodic table. It's got 2, 4, 6, and then 7 right here. So that's got a -1 formal charge. So I'm actually just going to put minus right here. And then this oxygen also looks the same, right? So now let's look at this chlorine. Chlorine's in the 7th group on the periodic table, so it wants 7, okay? But now, what does it actually have? It's got, let's see, 2, 4, 6, 7. This chlorine right here, the first one on the top here, that's not the center of chlorine, does have 7. So that has a 0 formal charge. So I'm actually just going to leave the 0 off just because we're only going to write the ones that are non-zero, okay? Now, let's look at the center chlorine here. What does it want? It wants 7. It's on the 7th group of the periodic table. What does it have? It's got 1, 2, 3, 4, 5. Okay, so we got 2 plus. Now, what do you notice? We have a 2 plus charge here on the center atom and 2 minus charges. So what we can actually do in this case is minimize these formal charges by making more bonds. I'll show you what that looks like here in a second. So earlier we've been making bonds by erasing other lone pairs, but in this case what we're going to do is we're going to use the lone pairs to minimize the formal charges without erasing any. So I'm going to actually bring one of these lone pairs down to make a bond, so that way we could share a little bit with the chlorine. So I'm going to change that here. I'm going to move this lone pair down. Boom. Now if I redo the formal charges here, you'll notice that the formal charge on this oxygen now becomes 0. So this is actually favorable for both parties, because if you look at chlorine now, chlorine wanted 7, right? It wants 7. Now it has 1, 2, 3, 4, 5, 6. So now it has 6. Now we've reduced the formal charge. We're minimizing it, right? And you can kind of see now that where I have this other oxygen with a negative charge, I'm actually going to do that again. So now I'm going to bring this lone pair down, share it with the chlorine. And doing that will reduce both formal charges. So now I've got a 0 on this oxygen again. And if I do this, if I count it again for chlorine, I've got 2, 3, 4, 5, 6, 7. Okay, so we're good. We've not only have we drawn the correct Lewis structure, we've actually minimized formal charge on this Lewis structure, because there are no non-zero formal charges, which is exactly what we want. So this should be your answer. So now the question is, do either chlorine's atoms have an expanded shell? Well, let's look. This chlorine right here has 8 electrons, so no, it doesn't need to expand its shell. But if we look at this chlorine, it's got 2, 4, 6, 8, 10, 12 electrons in its valence shell. Okay, be careful. I'm not counting what we're assigning to it as a formal charge. I'm counting what it has in its valence. Those are two different things. Okay, and in this case, it's got more than 8, which means it does have an expanded shell. So what I'm going to do is say center chlorine. I'm going to say center chlorine has expanded shell. Okay, oops. We'll just say expanded shell. Okay, it's got 12. It's got 12 electrons in its valence shell. Okay. All right, last one. So which of the following contain an atom that does not follow the octet rule? So for your convenience, I've rewritten the Lewis structures, but I've added in 5 and 6 here that explain the formal charges and placing the most electronegative atom or charge on the most electronegative atom. So I'm not going to use it a ton, but it's for your convenience if you want to look at this while we're drawing the Lewis structure. So I've got 8 valence electrons here, 2 times 7. 8 plus 14 is equal to 22 valence electrons. So I'm going to assume xenon is the center atom, because if you look at xenon, even though it's a noble gas, this is kind of a funky exception to one of these rules. Noble gases already have their happy octet, right? So we don't usually think of them as bonding in anything, really. They usually just exist as a gas, and they don't make bonds. But in this case, xenon, because it's far down in the periodic table, it's more likely to make extra bonds when it can, as long as it maintains a 0 formal charge. So I'm going to assume that xenon is the center atom because it can make the most bonds by expanding its octet, even though we can't do it without, right? Xenon by itself, without expanding its octet, has a full octet. So we wouldn't be able to make anything of it. So, and then fluorine, remember fluorine, those only got one area where it can make a bond, and it can't expand its octet. So we can't put fluorine as the center atom. So I'm going to put xenon here, and then fluorine, give everybody their octet. Okay, match the octet number. So here's 16, 18, 20. I am actually short here, which is a rare occasion. Okay, so I actually have 20 here, and I need 22. So when you come to this kind of a situation, what you actually need to do is add another lone pair on the center atom. Okay, and so this xenon will actually have 3 lone pairs, and that way you match your valence count. Okay, and then if I look at the formal charges, the formal charge on this fluorine, remember, wants 7, has 2, 4, 6, 7. So I'm going to put 0. This xenon wants 8, right? And it's got 2, 4, 6, 7, 8. So I'm actually good. I'm actually minimized the formal charge on the xenon. Let me go ahead and redraw these so they don't have all the lines through them. And that's got a 0 formal charge. And then we did the same thing with the fluorine on that side, right? So I'm just going to say 0 right here. So this is actually the correct Lewis structure. So now what they're asking is, does it not follow the octet rule? And the answer is yeah. I'm gonna circle this because it's one of the 3 options that they gave us, and it doesn't follow the octet rule because this xenon had to expand its octet. Right now, it's got a total of let's see, 2, 4, 6, 8, 10 valence electrons. So yeah, this is definitely one of those. Gallium trichloride. So now I got gallium wants 3. It's right here. Whoops, I almost circled germanium there. Gallium is right below aluminum and boron there. So it's in the 3rd group, wants 3 valence electrons. And then I've got 7 for each of the chlorines, and there's 3 chlorines. So there's 21 plus 3 is 24. 24 valence electrons. So now I'm going to draw my skeleton. I've got gallium, chlorine, chlorine, and chlorine. Give everybody an octet. Okay. And now I got to see if this matches the 24. So I'm going to say 8 or 16, 24, 26. So actually, in this case, what you're going to do is you're going to take away a lone pair from the center atom. And here's why it's favorable to do that. Because gallium is in the 3rd group on the periodic table. Okay. Not only does it get us to the 24 valence electrons we need, but if you look at the formal charges, remember chlorine wants 7. In this case, it's got 2, 4, 6, 7. So I'm going to put a 0 formal charge for each chlorine. But if you look at the gallium wants 3, and it has 1, 2, 3. And so because of that, it actually has a 0 formal charge, and it will be happy that way. Gallium and boron are the ones that are kind of the ones that you'll see most commonly associated with that. You'll actually see that here again in part A, where they'll only accept actually 6 valence electrons, and they're happy with doing that because that way their formal charge is 0. Okay. All right, and then last one here, we've got O and F. So I'm going to put O and F, draw my skeleton, and then give everybody an octet. Okay, now I'm going to count 6 plus 5 plus 7. I've got, that's a total, let's see, of 11, 18 valence electrons. So here I've got 8, 16, 18, 20. So I've got 2 extra valence electrons. And remember, we're just going to make a bond out of this. So I'm going to say erase those 2. Let me go ahead and put this lone pair in a better place. Okay, so now I've got a 0 formal charge on that oxygen. Remember, 1, 6 has 2, 4, 6. Okay, this nitrogen, remember, has its lone pair now, so it's probably going to be a 0 formal charge. And this fluorine has a 0 formal charge. And if you notice, they all have their octets, right? Nitrogen has its octet right here, fluorine has its octet right here, and oxygen has its octet right there. So this one actually doesn't break the rule. So in terms of the ones that break the rules here, it's going to be 1 and 2 only. Okay. All right. I hope that was helpful. We're going to be in the next video. We're just going to be cranking through a few examples here. I've chosen about 5 that we're just going to be using these new rules to depict the correct Lewis structures. Okay. We'll see you in the next video.